Oh yeah. Good day, welcome back to another episode of Explosions and Fire. And today, God, there's one thing that's been requested so many times over the years for this channel. Everyone wants to see chlorine trifluoride, and for good reason. Chlorine trifluoride is an amazingly dangerous molecule. It's an aggressive oxidizer. It releases fluoride ions, makes hydrofluoric acid, which is tremendously deadly, intensely corrosive. Although there's been all these stories about it, over the years there's been hardly any pictures or footage of the actual molecule or any reactions of chlorine trifluoride. Of course I wanted to make it, but it's just not something I can whip up here in the shed. The toxicity of chlorine trifluoride alone would make it, not something I could do, but this is something that ignites on contact with most materials, requires fluorine gas to make, but it is used as a chemical in some industrial processes like the semiconductor industry. So in the back of my mind, I always thought, what if I could go somewhere and film someone else doing chlorine trifluoride? So imagine how excited I was that there was this German professor, Professor Florian Krauss, who had chlorine trifluoride in a cylinder and wanted to make YouTube videos, and he invited YouTubers to come and film, and I wasn't invited. Okay, no, I can't lie. I was definitely invited. Nicholas from Advanced Tinkering, a super nice guy. He definitely invited me, but I said no. I mean, Germany's a long way, right? It's far. I'm disorganized. I have a real job still. No, I can't do it. But then I was thinking about it, right? Like, this is something I've wanted to do for a decade, and I was just letting other people do it. So I thought, should I ask to be re-invited? Nah, that's too awkward. Surely I can do better though, right? Can I just beat chlorine trifluoride? Can I make something more reactive than chlorine trifluoride? Can I make something with more fluorine than chlorine trifluoride? How? How would I possibly make that? What lab in the world would possibly compete with the prowess of an advanced German fluorine lab? That's right, a different German fluorine lab. Let's go to Germany. Hell yeah, slightly different place. Let's go. Yeah, guten Tag or whatever. Yeah. So I'm here today at the Free University Berlin. I'm here to see one of the few labs in the world that routinely uses pure fluorine gas.
So welcome to our fluorine lab at the Free University in Berlin.
Thank you.
So here in Berlin we have a special collaborative research center for fluorine-specific interactions. So this means also that we do a lot of fluorination reactions.
We're here to do an experiment I've always wanted to do, but obviously I'm not capable of doing in my shed. So I've come here.
One interesting molecule, which is quite seldom, I would say, is fluorinated peroxide.
FOOF is an extremely reactive molecule. That's going to be pretty obvious. You can't buy it, but you can't even really store it. It will decompose into fluorine and oxygen, even at liquid nitrogen temperatures. It's a pretty hardcore molecule.
So how we will prepare today the F2O2? Now this is quite easy if you have the proper equipment. So we are in the fluorine lab, so we have elemental fluorine, we have also elemental oxygen.
You simply just take liquid fluorine and liquid oxygen, blast UV light into it. I will be getting a bit of help to do it. Okay, no, I'm legally not allowed to touch any of the equipment.
This is Niklas and I am Gesa, and we are PhD students in the Riedel lab. We are focusing on halogen chemistry. Niklas is mainly focusing on fluorine chemistry and I am working in chlorine chemistry.
But I will be there, and I'm worried that just my presence in the room will make the chemistry stop working anyway, so... FOOF is another one of these highly reactive molecules that's sort of entered the public consciousness, I think mostly in part because of its name, but it is a super reactive molecule. It has definitely been made before, lots of times over the past decades, but one of the things I find so interesting about molecules like this that are so widely known is that there's no pictures of it. Maybe because it's so rarely made, maybe because it's so dangerous. Even on the Wikipedia page, it lists two different colours, really, well, sort of conflicting colours. So that's our mission for this video and why I'm at this complicated slank line that's dedicated to fluorine gas. We're trying to see if we can make some FOOF, maybe do some reactions, but also just see what it looks like. What does this thing look like?
First of all, for the line setup, so we have like here the cooling trap. From here down there we have like a very powerful pump, And then here the vacuum goes through this soda lime tower here with a scroll pump. Which is quite good because like some fluorine gets to the oil, then it would just like immediately burn. Wouldn't be the best. We have like some residual fluorine. We pump it over the soda lime tower. In the soda lime tower, the fluorine or the HF reacts with mainly the calcium oxide to form then calcium fluoride. Then we have like here the line setup. Where we have then different attachments.
Yeah, so it's because it's stainless steel and then the fluorine reacts with the internal metal and makes a non-reactive layer.
Exactly, like a passivated layer. Here is our fluorine valve, and this fluorine valve is connected to a small fluorine bottle, which is inside this cage here. We don't have to open it with a hand, with a valve. We have like this tool which you can just stick here inside. Then you have like the elemental fluorine. Then you can just open the valve and then you have the fluorine in the line. If you are careful and you really think through what you want to do, then this is something,
But you must have got it wrong at least once, right?
Yeah,
but
sure.
yeah.
Sure. I mean, everybody makes mistakes, and if something goes wrong, there's usually some way to cover it up, or like to not cover it up.
Mitigate or
fix it.
So for our first food synthesis here, Nicholas has pre-mixed fluorine and oxygen gas.
This is already filled with like half a bar of oxygen and half a bar of elemental fluorine.
And we're going to condense it into its liquid form with liquid nitrogen and pump hard UV light into it, and that will cause it to react into the foof. An obvious question is, what on earth are we going to use as a reaction vessel? While the stainless steel will all passivate, we can't use that as a reaction vessel because we've got to put the UV light into it. The answer is actually PFA tubes. It's a fluorinated polymer, so quite a common material, but it mostly stands up to the fluorine and the foof.
Not the most beautiful one, but
Yes.
should be close.
I say mostly because not always, but yeah, we can use them to condense liquid fluorine and liquid oxygen in a mixture together. Oh yeah, look at that. Yeah. Still going to have to put in a lot of UV light though, so we've got a very powerful UV lamp. It's kind of scary how much light comes out of something like that small,
it's crazy.
isn't it?
It's like,
Have you ever had one explode on you?
No, not yet.
No, not yet. We've still got to cover the fume hood in paper so we don't get blinded, and still wear glasses for safety. It's a lot of light.
And now we are ready to turn on the UV lamp. Then like this we already see, we saw it quickly on the camera that it turned on. In the beginning it's not as strong. When it heats up, then we have like the full UV radiation.
The camera sees a lot of green and it's putting out a bit of green light, but for as much green light it's putting out a lot more hard UV light, which the camera doesn't see. And we also don't see because we're wearing the glasses, which is good.
I think it looks quite good.
But yeah, the reaction vessel is exposed for 2 hours to try and convert these two gases into the foof. But after the 2 hours is up, we can turn off the light, pull back the screen and see. It's definitely changed colour. Oh yeah, I can see it's slightly a different colour.
Change, right?
Looks like it actually worked. Sorry for doubting it. We've actually made the reaction happen.
We now have here a mixture of like this solid foof in combination with like still liquid oxygen and maybe liquid fluorine. Therefore, we just apply vacuum. The oxygen and the fluorine, even at liquid nitrogen temperature, still have a vapor pressure, so we can remove them in the vacuum. Okay, now we can see that the pressure is down at 1 millibars here. So that means that we have not removing any volatiles anymore. We can close our reaction vessel and then we can remove the dewar to see the foof for a moment. And here we can see the nice reddish orange color of the foof.
Yeah. So here we go. Here's the colour of pure solid foof. Yeah. It's a vibrant orange-red colour. But really, we've got to see some reactions with it. How reactive is it? Yeah, fantastic. Xenon is usually a completely inert gas, and we're going to be reacting it with our FOUF at basically liquid nitrogen temperatures.
If we condense now the xenon, first of all, nothing will happen. Xenon will just freeze here at the top and it won't be in contact with the FOUF. But then if we remove the cooling, then the xenon gets into the gaseous form, and then the FOUF and the xenon will react with each other.
And it might explode is the key bit. Well, you said it probably won't explode, but you handed me hearing protection anyway.
Yeah. This reaction has some potential to ignite, and when like one of these PFA tubes or like their reaction ignites in there, we're not 100% sure what happens there. So they hold a bit of pressure, these tubes. You can go usually up to 5 to 10 bars in these. If it's too much pressure, it might rupture, and then it's quite a lot bang. Now we have like the white xenon here condensed. Okay, we'll remove now the liquid nitrogen, and then let's see what happens.
Okay, so the tube didn't rupture, I'm sorry. It reacted very quickly after you took it out, didn't it? It didn't need much heat
No.
to start.
So now we just let it come to room temperature.
But we've just made xenon tetrafluoride, a reaction that if you tried to do it with fluorine gas requires hundreds of degrees worth of temperature and then still doesn't work very well. So the FOUF is so much more reactive than fluorine, which is a little bit frightening.
We will remove the xenon. Maybe I shouldn't say this because it's like a waste of chemicals, right?
It's alright. Alright, we're a little bit embarrassed to dump the xenon tetrafluoride just into the trap and destroy it here. Xenon tetrafluoride is a very cool molecule. It's hard to make, and we're just wasting it here. But also, wasting xenon feels a little bit... I mean, have you ever read the film Dune? In that, there's the spice, which is a drug that they predominantly use to enable space flight. Xenon is a drug that no one really knows how it works, and we use it for space flight, and it's very rare. This joke doesn't really have a punchline. It's just something I think about sometimes. So that's FOUF, an extreme oxidizer, but it does leave you with a question. Can we do better? What is the most oxidizing thing ever? Can we make it? The molecule we want to make is platinum hexafluoride, which features platinum in the +6 oxidation state. And to make it, we simply need to burn platinum wire over liquid fluorine in like a pressurized fluorine reaction vessel. So it gets up to pretty reasonable pressures, right?
Yeah, so if you would let this come to room temperature with all of the condensed platinum inside, then yeah, there would be a lot of pressure inside. Like at liquid nitrogen temperature, there's a moderate pressure, which is fine. Fill the elemental fluorine in here. Now we can add the liquid nitrogen here. Fill it with elemental fluorine again, condense the elemental fluorine in, then add some more elemental fluorine so that we really have an excess of the elemental fluorine.
But now the platinum wire is stuck inside that reaction vessel. How on earth do we ignite it?
So now we should have enough elemental fluorine inside.
It's car battery time. It's car battery time.
It's car battery time.
Yeah. There are definitely other devices that will generate current to heat a wire to ignite this platinum.
And then get this nice car battery here.
But the procedure Nicholas is following specifically mentioned a car battery, so he specifically went out and got a car battery with jumper leads for this experiment, which I love. We set it up, connect it all, and just hope it works.
That's basically it. You don't really see anything. Thanks for your attention. That's it.
Yeah, that's it. All right, let's go home. Because we can't see, we just expect it to fill up with platinum hexafluoride. So while applying a vacuum while at liquid nitrogen temperatures, all the residual fluorine got removed, but as it warms up, the platinum hexafluoride has a vapor pressure, so we should also be able to condense over some platinum hexafluoride.
We can remove now the liquid nitrogen so that the PTF6 slowly warms up, gets to a certain point where it has a vapor pressure, and then it will condense out of here into our PFA tube. So let's do this.
And it should be coming over, but it didn't. Nothing really came over, even though it should have.
I have to say I'm a bit concerned that something didn't work as planned.
Was it the car battery? Were we blaming the car battery?
We are blaming the car battery.
Oh, it's a bloody car battery.
The bloody car battery.
Oh, yeah. All right, so this is attempt 2, right?
Yeah. We don't see any sparks.
So yeah, we tried it again, doing exactly the same thing, and yeah, spoiler, it also didn't work. After years of doing things in my shed, I'm very used to things not working, but you can tell this German lab is not used to things not working. This might be the first reaction that's ever failed for him. I mean, that's not true, but it certainly felt like it. Anyway, the assumption was that the platinum wire had fallen off the electrodes, so it wasn't getting the current through. So when we eventually took it apart, we saw that everything was actually completely fine, so it wasn't that at all. Sorry. That was surprising.
Nothing happened.
We're back, because the important step of the synthesis was
go
get a kebab.
We had a lunch break, which was very important as well.
Yes. So after a dinner kebab break, we decided on a third attempt, and this time we decided to do really the scientific approach to troubleshooting on a third attempt, which is to do exactly the same thing you did on the previous 2 tries, but really think it should work this time. Yeah, and we've decided it will work.
Okay, but this is maybe a good time.
And all that positive thinking, and also maybe charging the car battery up to a better level, but ignore that bit, made the reaction finally work. We ignited the platinum wire inside the fluorine atmosphere.
To start removing the elemental fluorine first.
Oh yeah.
Is there like a slightly yellowish color there?
Yeah, probably right? Yeah.
When we remove the liquid nitrogen dewar, then we would expect that it forms like a deep red color there.
And when we applied the vacuum after all the fluorine was gone, we started to see platinum hexafluoride come over and be condensed in our PFA trap.
Oh yeah.
Okay, a little bit of background. Oxidizers want electrons, right? Oxidizers want them badly, they need them, right? That's what makes an oxidizer. And a measure of how powerful an oxidizer is what's called as electron affinity. How much energy is released when that oxidizer finally gets this electron? There's heaps of it in there. For oxygen's a reasonably good oxidizer, and it has an electron efficiency of 0.45 electron volt. The fluorine, which is an extremely aggressive oxidizer, is just over 3 electron volts. So platinum hexafluoride, you would think if it's more oxidizing than fluorine, would maybe be like 4 or 5 electron volts. It's actually 8. It really wants an electron. And we are going to use this most powerful oxidizer to recreate an experiment from 1962. At the start of the 1960s, chemistry, I mean, it's pretty advanced. It's not that different than it is now. But one of the ideas at the time was that the noble gases simply wouldn't react with anything. I mean, why would they react? They've got full electron shells and the ionization potential, so the amount of energy needed to remove an electron from the shells is just too much energy. You're never going to have an oxidizer powerful enough to achieve those energies to pluck an electron from a noble gas. At the time, no one had managed to get xenon to react with anything, and xenon had been known for more than several decades, and people had tried various reactions, even with fluorine gas, but they've never saw any reaction with xenon. This was until Neil Bartlett in 1962. So Bartlett had been playing around with platinum hexafluoride. Well, I mean, as much as you sort of play around with platinum hexafluoride, but he decided it was probably reactive enough to react with xenon. Working basically alone, he learnt glass blowing to make this intricate apparatus that would react instantly the platinum hexafluoride and xenon. He would fill the bottom compartment with the hexafluoride, use a glass blowing torch to seal it off, fill the top compartment with xenon, and then there's a little glass window that he would turn the apparatus, some ball bearings would fall down and shatter it, and the two would instantly mix. In doing so, he was hoping to maybe see a color change that indicated a reaction. When he performed this reaction, this is exactly what happened. It turned from a vibrant red to a yellow instantly, and for the first time in human history, a noble gas had been successfully reacted. Bartlett was obviously very excited having seen that beautiful color change, and apparently he ran out in the corridor to tell people about this fantastic reaction, but no one was there because he was doing this reaction past 7 p.m. on a Friday. Don't do that. For starters, if you make a discovery that's going to get you nominated for the Nobel Prize 3 years in a row, and you do it past 7 p.m. on a Friday, there's no one's going to be around to celebrate with you. And secondly, if you die, the cleaning staff have to find your body, and they already put up with enough shit from your lab as it is.
This is like the original design.
Yeah, you didn't want to change it.
The only thing we actually changed is that we use now here glass. In the original apparatus, Neil Bartlett used like stainless steel balls here, then just moved it like this, and then it went down like this. Hopefully it destroys the glass layer and we can see the new compound. Let's pray. In principle, it isn't a problem if the PTF6 is getting to the glass. Nothing should happen there. If you store it there for a short time, if you would do it for a quite long time, then it would be a problem indeed. We eliminated now all of water by adding the elemental fluorine. It's a nice way to dry your glassware, by the way.
So by applying a vacuum to the glass apparatus, we can pull in some of the platinum hexafluoride and condense it in the bottom with liquid nitrogen.
Can you see it?
Yeah.
I hit it like a bit. Now we'll open this again. Oh yeah, oh yeah,
Oh,
nice,
yeah.
nice. It could actually be enough already. Let's wait until everything is condensed. So I think now everything is condensed.
And then comes the hard part where we got to cut off that glass passage with a glass blowing torch to seal off the extremely aggressive oxidizer inside a sealed glass vessel.
Yeah, so let's see.
Right, because it's just going to close under the vacuum pressure itself.
Yeah,
right.
yeah.
Easy. In principle, as you'd say.
In principle, yeah.
I was happy to just watch this bit because, knowing my torch skills, I would have destroyed everything. But it looked pretty good, the seal. Woo!
Okay.
We felt reasonably confident in our glass pipe bomb, so we got to fill the top of it with xenon gas.
So now we have like 1 bar of xenon on this top part here. The PTF6 at the bottom.
So you're letting that warm up.
Yeah,
room temperature.
We let it warm up first.
Hopefully it holds.
Hopefully it holds. Yeah, it should do.
Once it was filled with xenon, we got to close the valve, take it off the line, and finally shatter that small glass window that would allow the xenon to mix with the platinum hexafluoride.
3, 2, 1. Is the torpedo through? I don't know.
You wanted a big flash of sudden colour change, didn't you?
No, it's it's fine.
No, it's fine.
And I'm happy about it. I'm not 100% happy. Because it looks sealed, actually, but right?
Yeah, there was obviously no colour change as the window was smashed because the reactant flask was already yellow. So we think that some xenon leaked in through that glass joint. All right, we're talking about something extremely reactive here. It was orange when it was cold, and by the time we warmed up and we got it off the line, it was already yellow. So some xenon somehow leaked through that glass seal. I guess it wasn't 100% sealed. Yeah, this was always going to be a difficult reaction to get right in the first try. We've got a backup one. But luckily, the glass blower had made up an entire second reaction vessel for us to try it all again. Let's pretend we just did that past 7 p.m. on a Friday and no one saw us do it.
Oh, there we go. Yeah. Yeah, it was all clogged up with the, yeah. So the stick really did help. In your opinion, which is harder, chemistry or using the torch?
Using the torch.
Using the torch, all right.
Surely attempt 2, we've mastered things. What could possibly go wrong? Okay, we're not glass blowers. We shattered the glass. Only a small hole, but it's enough.
What happened?
We get to now see a very cool molecule. Instead of the xenon salt, we're going to actually make the O2 salt. Platinum hexafluoride is so oxidizing that it's going to oxidize O2. We're actually making a salt out of O2 plus. So yeah, that was the recreation of the Bartlett experiment, if he was slightly more unlucky. So maybe the secret is doing it at 7 p.m. on a Friday. I'm really caught up on the 7 p.m. on a Friday. I will not be made to feel guilty as an academic for not working at 7 p.m. on a Friday. I'm going to the pub, and I shouldn't feel bad for going to the pub at 2 p.m. on a Friday, okay? You gotta set work-life boundaries, all right? And that boundary is 2 p.m. We're back, and now we're doing it the modern way. Because the old way,
exactly.
A little bit difficult.
Technology has improved. As you can see, here's the remaining PTF6 now in this tube. And we now added xenon to our stainless steel line. And when we open now this valve very slowly, hopefully we can see that the color changes to like this yellow color of the Xenon Plus PTF6 salt. Camera ready?
Camera is not quite ready. Sorry, camera's incompetent.
Now I will open it. Oh, nice.
Right. Wow, that's it's a really quick xenon reaction.
Yeah.
Good work.
It's-
Valves, you know? Modern valves.
It's amazing what they can do. If you imagine now the PTF6 with like other substances, like it's it's incredible.
So that nearly brings us to the end of my time in Berlin. But we wanted to try one more experiment with food.
No, I think it's done.
This time, we haven't pre-mixed the gases, so we have to load in the pure fluorine gas and then the pure oxygen gas.
And here we can see there's the elemental fluorine. That's the yellow color.
Yeah.
It's beautiful.
Beautiful. It's a horrible yellow. It looks scary.
Yeah.
Looks
But I think
Which one do you like working with more, liquid fluorine or liquid oxygen? You like the liquid fluorine?
actually liquid fluorine. You know what to expect. I like the controlled conditions of the liquid fluorine more than of the liquid oxygen.
And we managed to get it so that the two gases floated on top of each other, which I thought was very cool. You can see the oxygen up the top there. It's just a frightening thing to see.
It's frightening. Absolutely.
Okay. But I think it looks good. Yeah, I think we have a good amount. Start.
After another 2 hours of UV exposure, we have a new batch of solid foof.
New batch.
And this time, we're going to react it with chlorine gas. We're going to react it together the same way we did with the xenon. So we're going to condense the chlorine at the very top. It's going to solidify, and then we pull away the liquid nitrogen, and the two will interact very slowly and at cold temperatures.
Now we will condense the chlorine inside this PFA tube, close it in and let it come to room temperature so we hopefully see a reaction.
Is there any chance of any chlorine oxide formation, by the way?
Yeah.
Chlorine gas is an aggressive oxidizer, so usually it's the oxidizer, but it's not the oxidizer in this case. We are, of course, going to be making chlorine trifluoride directly from foof and chlorine gas.
We can see the yellow chlorine condensing here
Oh yeah.
at the top. Now we still have the foof at the bottom. We will remove it now and let it slowly come to room temperature, and then they will directly react and form the ClF3.
Once again, hoping that the reaction doesn't generate too much heat to boil the reactants, because that will generate enough pressure to burst the tube, which will be loud and spray extremely corrosive chlorine trifluoride everywhere. As much as you probably want that to happen, we didn't really want that to happen when we were forming it. It is pretty hard to see with all the condensation on the outside of the tube, but the reaction is instantaneous. As soon as a droplet of chlorine hits the foof, it instantly makes chlorine trifluoride, which we see at the end as this horrible yellow liquid.
Now we can see something yellow forming at the bottom, and this is actually the ClF3.
Oh yeah, you can see it splashing around in there.
Before long, couple of minutes, it's evaporated away, it's gone, but we did it. We made chlorine trifluoride. So, the important bit, once again with these videos, is that we survive them.
So are we going to try it again, or are we going to go to the keg party?
Try it again!
Yeah. Oh no! Wrong answer. This is the one, this is the one. This is the one, this is the first shot.
I'd very much like to thank Professor Dr. Riedel for his invitation to come to Berlin. And especially thanks to Nicholas and Geza for running through the experiments, actually doing the experiments. And thanks to everyone at the Free University Berlin for just being good fun and hanging out. Thanks to Patreons for allowing me to fly to Germany to bloody film stuff and still not having to take a sponsor. And also a final thanks to Florian Kraus for having me in his lab as well. I know I said I wasn't really invited. I just kind of went anyway in the end of it. So I saw these other YouTubers filming their fluorine stuff. If you want to see some more fluorine chemistry, there's some fantastic channels, Advanced Tinkering, Elias Experiments, some fantastic content coming out. Oh well. Back to it, I guess. Next video. Let's do it. What are we doing next? Haven't even finished this one, but we've got to, what's the next? What's next? What's next?